Okay, this is a video on how to calculate the centroid location for a two-dimensional area. Okay, why would you want to know the location of the centroid of an area? It basically is the balance point of a two-dimensional product, like maybe a sheet of plywood. You know, it's not really two-dimensional, it has thickness, but for our intents and purposes, it's two-dimensional. And the centroid location would tell you where you could pick up that piece of plywood with a single rope, you know, and it would be suspended level. Um, that's kind of an obscure requirement. The real reason you need the location of the centroid is because it is the stepping stone to getting what's called the area moment of inertia. And the area moment of inertia is a property of a cross section that describes how resistant that cross section is to being bent. Okay, so we'll use area moment of inertia and strength of materials and so on. So, all right, the centroid location for common shapes, like simple shapes like squares and rectangles and circles, is easily determined just by inspection. For instance, if you have a square, it's obvious that the centroid's right in the middle. Okay, so if you have a square, it's say 6 units by 6 units, whatever those units are. Then this distance from here, right, that distance, we call that x bar, is 3 units. Okay, and similarly, the distance from this bottom left corner, which I'll speak more about in a minute, to the horizontal centroidal axis is y bar equals 3. Okay, so that's easy enough. You don't need math for that. Circle's even easier, of course. You have a circle. The centroid's right in the middle, to the surprise of nobody. Okay. That's not the problem, really. The problem is, when is the area not a simple shape, not a rectangle, a circle, and so on? Okay. What if the area is a T-section like this? Well, I mean, the centroid is going to be in the center span. You know, it's going to be midway between, because there's a symmetrical axis, vertically. But in this direction, with regard to a horizontal centroidal axis, it's probably up here somewhere, but we can't say by inspection. We don't know where it is. We don't know where it is, but we have to know mathematically where that is with precision. Okay, let's do an example using the formulas for centroidal axis location. Let's use a T-section. Okay, let's just make a T-section. I'm just going to propose something here. I'm just randomly making one up here. Okay, let's make it 2 units thick there, 2 units thick there. Let's make this 5 units, like this, 5 units high. And let's make the total height 7 units, 7 centimeters, 7 inches, whatever. Okay, and let's make it 7 units wide, like that. Okay. All right. Again, the location of the centroid, we kind of know where it is, and I'm just gonna place it on here, but we have to determine it with precision. But let's denote datum, and the datum is basically where are we going to measure the distances x bar, y bar. The centroid is a centroid is a centroid. There's no alternative. It's right. There's only one centroid, but the question is, where are you going to measure it from? What's your frame of reference? Well, pretty much every question uses the bottom left corner of the image, or the bottom left corner of the anchor point, like that. So I'm going to use that point right there. Why would we use that XY like that? Why would we say that? Why would we overlay the XY axis in the bottom left corner? Because by doing that, the location of the centroid will be positive values. The distance, the horizontal distance from the Y axis to the vertical centroidal axis will be a positive number. Similarly, the vertical distance from the x-axis to the horizontal centroidal axis will be a positive number. We could have chosen this point as the datum in the top right, but then those distances to locate the centroid would be negative values. We don't really want to have negative values if we can help it. Okay, that's the first step, to locate the datum down here in the bottom left. You can try it from the bottom right if you want. Just watch the negatives. Okay. Now we have this equation for x bar and y bar. X bar is the summation of AI, y bar I, whatever that means, over the summation of AI. Okay. This is saying take a complex shape and split it up into two or more simple shapes, which are easy to analyze by eye, basically. Okay. What do I mean by that? Well, this T section, the T by itself is not a simple shape. If it were, we wouldn't have to do this mathematics. But the T section is comprised of two different simple shapes. And I'm going to split it up this way. I'm going to say, well, let's call that area 1, and let's call the one on top, the top flange, area 2. And now we split it up into two areas. So this I placeholder is just a mathematical subscript, meaning any number of areas from 2 to infinite, okay? Here we go. Let's execute this. X bar. This should be X, sorry. No, Y. X bar I. My mistake. There we go. Okay. All right. So it's area 1. This is area, so the product, area 1 times X bar 1 plus area 2, X bar 2. That's how to read that. Here it is expanded. Area 1, X bar 1 plus area 2, X bar 2. That's how that expands out. And the denominator, some of the areas, well, area 1 plus area 2. Okay. All right. Normally you wouldn't write that equation, but that's what that looks like. I would just normally go right into the number entry here, but okay. All right, let's go down here. X bar equals area 1. Well, area 1 is this vertical part. It's 2 by 5. 2 times 5. That's area 1. X bar 1. X bar 1 is this distance right here. Here's the centroid. It happens to be right where I wrote the number 1. Here's the centroid location of just area 1 by itself. And X bar 1 is right here. X bar 1, like that. Okay. Well, X bar 1 by inspection is 3.5. It's half a 7. In fact, I'll put it down as 7 over 2 like that. That's X bar 1. Okay. Area 2, that's the top flange. Well, the area of area 2, the top flange, is 7 by 2. 7 times 2 units. And X bar 2, the centroid location of area 2 is right in the middle of area 2 like that. Well, it's the same X bar. It's 7 by 2. You realize the calculation of X bar is not necessary here. We could just do it by inspection, but I'm just demonstrating the use of the equations, okay? So it's 7 by 2. And the sum of the areas, well, the areas, that's the total area of the component, if you will. Summation of areas, right? Area 1, well, you have that calculation done. Area 1 is 2 by 5. So just extract for the denominator, area 1 plus area 2. Just pull them down from the numerator. 2 by 5 plus 7 by 2. Calculate that number out, of course, right? It's obviously going to be 3.5, but here's a calculation, okay? Here's a calculation. The more interesting calc is Y bar, but here we go. Okay, shouldn't show you my password. All right, here we go. 2 times 5. Let me turn this light off. There we go. 2 times 5 times 3.5 plus 7 times 2 times 3.5 divided by 2 times 5 plus 7 times 2 is 3.5. No big surprise there, 3.5. Okay. The more interesting calculation is Y bar. Y bar is right. So here's X bar. I'll you know what? I'll draw an image after the fact. Let's do Y bar here. Y bar. Y bar is sum of the area I, Y bar I, over the sum of the area I. Okay. I'm going to do it in a one-liner here. Okay. Y bar area 1. Well, area 1. Here's area 1, the lower area. Let's give me a little thing to area 1. Y bar is this distance for area 1. It's from the datum, right? Y bar 1. It's half of 2.5. So area 1, same area, 2 times 5. So there's some redundancy there. It's the same area as up here, 2 times 5. And Y bar is halfway up the central rib, 5 by 2. Okay. Area 2. Here's area 2. It's a top flange. Y bar 2 is to the midpoint of that. And the diagram's getting pretty messy. I wouldn't normally overlay all these dimensions on there, but I'm trying to convey, you know, the approach here. Y bar 2 is not 7, careful, it's not 5, not 7, it's 6. The midpoint of that top flange is 6 units up from the bottom. So area 2, 7 by 2. Y bar 2, 6. Okay. Summation areas, same as that. Once you've got the area summation for one calculation, you've got it for the other. The denominator is the same for both X bar and Y bar calcs. Okay, do that calculation. The numerator, 2 times 5 times 2.5 plus 7 times 2 times 6 divided by 2 times 5 plus 7 times 2. 4.542. Y bar for the whole thing is 4.542 units up from the bottom. Okay. What's the summary look like? Here's the summary, because that's kind of a messy drawing. Here's the summary for this T section. Okay. For this T section, we have this going on. Okay. 2, 5, 7, like this. Just get some overall dimensions on there, like that. 6 wide, or sorry, 7 wide, like that. Okay. The centroid is as we suspected. The centroid's up here somewhere, but now we know exactly where it is. Here's our datum. Okay. Let's call that the original y-axis. Here's the x-axis. Overlay them. Here's a 0. That shouldn't be. There's no y bar. It's x. Just y by itself. It's x by itself. Okay. And here in red is x bar. Okay. X bar and y bar is here. Let's do it here. Y bar. Okay. X bar is 3.5 units to the right of the datum. 3.5 units over. Y bar is 4.542. That one, there's no way to do that, right? 4.542 units up. We now have with high accuracy, exactly, precisely what that area or where that central axis is located. Okay. That's it.